Okay, great. Alrighty, let's get started. Thanks everyone for joining us today at the online AI Tech Talk series. I'm Bill, the host from AI Camp. Before we get started, just want to do a quick introductions on AI Camp. AI Camp basically is a global online platform for developers, engineers, and data scientists to learn and practice AI technology. With the mission of make AI available to all developers, we have grown to more than 50,000 engineers in the group globally. We have hosted more than 200 local tech meetups, workshops, boot camps. Also have the crash courses, and also have the large technology conference. So we live stream most of tech talks globally. You can take a look at the website. It's on the screen. So to see our upcoming tech talks, and also we have the boot camps, workshops, and other way of learning that we offer. By the way, you can type your questions at the chat window. The speaker will pick up to answer and discuss during the talk or at the end of the talk. And also if you want to say thank you, since I mute all of you, so if you want to say thank you or welcome, please, you can type over there. So today I'm very excited to have Umri to share and talk about the active learning approach to image image recognition. Umri is a lead scientist in machine learning at Figure 8 Technologies. He is developing machine learning, more specifically deep learning frameworks for various applications like object detection, segmentation, and classification in fields ranging from medical, retail, self-driving car, satellite, etc. He has 3 years postdoc experience at Harvard Medical School, where he developed machine learning and deep learning frameworks include the region of interest detection, nuclear and ground detection, segmentations and classification in 2D and 3D medical images, H&E stained, IHC stained, and fluorescence images. He got a PhD in computer science from University of Grenoble, France. Let's join us. Welcome, Umri.
Thank you for introduction. How can I share my slide?
You can give me a second. Okay, you can click the share screen at the bottom of the window.
Okay. Okay.
Yep.
Okay, so I will start my presentation. So the topic is an active learning approach to image recognition. So I try to apply the approach on a problem about parking sign detection in dense city. How big is the data? So this is a very nowadays very hot topic. So based on the current estimate, there is 2.7 zettabyte of data exists in a digital world today. By 2020, analysts predict the amount of data will be 50 times what it is today. In 2012, 90% of all the data that exists in our entire history had been created in the previous 2 years. Every 2 days, we create as much information as we did from the beginning of time up to 2003. Based on these type of status information, we need to find a better and more efficient way to analyze our data. There are 2 ways to label data based on budget and time constraint. One way, label faster and cheaper, in which machine learning and human in the loop approach is used to streamline and speed up the labeling process. Second is label smarter, which select the most informative row to label in order to optimize information and data volume. In order to train a machine learning model, there are 2 options. One, label the entire data set, and build your machine learning model once. It will require more time and budget, but not an efficient approach to label all data points that have similarities. The other way, semi-supervised way, with the iterative approach, start with small subset with high priority of data, and then use active learning approach to select more data by labeling and model building. And after the training of couple round of iterations, then we manually override this similar data. Here, there is a plot of presenting two models learning curve. X-axis represent amount of labeled data. Y-axis represent model accuracy. If you use all data set to label and build model, which give 97% accuracy, then we go with iterative approach. Each cycle with a blue color, a blue circle, and gray circle represent the model performance, which use a subset of labeled data to train. The first approach is active learning approach, which represent blue circle, and second approach is the semi-supervised supervised learning iteration, which represent the gray circle. You can see there is a big difference in the middle, where active learning approach perform much better than the supervised learning approach. Then I will apply my active learning framework to a problem which is called parking sign detection in a dense city. In a dense city, the biggest challenge is where I can park. Streets, we can find a lot of parking spot, and it's very tricky to find the relevant information, the day, the time, and the rules. How computer vision can help to improve parking experience and transportation environment. There are multiple publicly available street view imagery dataset like Google Street View, Microsoft StreetSight, MapJack, Everyscape. So we select the Google Street View imagery. They use 9-direction camera for a 3-degree view at height of 2.5 to 2.8 or 3 meters. They use multiple GPU units for positioning the 3G, GSM, and Wi-Fi antennas for scanning. And they also use 3G and GSM for hotspot. So they collect all this information and pack together in their database, so we can query and we can access those information. It's publicly available. Online street level imagery provides opportunity for developing new vision-based algorithm to detect, classify, and localize parking sign. Street level imagery contains different great information about parking rules that is located in the images needs to be converted into structured format to become useful. While online street level imagery database contains updated panoramic images of all signs, their potential for understanding on-street parking restriction at scale has not been fully explored yet. There's an opportunity to create a new vision-based algorithms that use this visual data to automatically detect and classify parking signs. Parking signs in a street of cities are very diverse and might include wide range of color, shape, and dimensions. The high intra-class variability and dynamic occlusions can significantly challenge the development of automated method. Other challenges are uncontrolled illumination, resolutions, image quality, and occlusions and confusion with man-made objects. Here's some example of messy words. You can see it's very hard to sometimes when there are such kind of signs in our streets. So we, as a figure 8, we have a sense that human in the loop with machine learning is a bad solution at this point. So it start with data collection. Download the panoramic images, because panoramic images are bigger in size, and we split into small chips, and then we label first subset of the data, either randomly, either some in an intelligent way to select the training set, and then we go build a model, and model predict on unseen data where is confident and where is not confident. Based on that information, we go again to human, label the data based on the feedback from the machine learning, and then again train the machine learning model. So this is kind of a loop, two loops together. One is human, other one is a machine, to try to optimize the solution. And the first step, on the left, there is a panoramic images. The size is about 13K to about 6.5K pixels. These are big images. So we chop up the panoramic into small tiles or chips. The size of these chips are 1K by 1K. Second part is we create a review job and launch on our platform to label is the parking sign in those chips or not. Crowd, they find the chips which have the parking sign. The second flow is when they find the parking sign in the image, then label a box around the parking sign. So after collecting the data, we also share these data sets publicly available. So on our figure 8 platforms, these data sets are publicly available. The training set that is publicly available is the first training set, and then we have a different round of iterations, and then the last training set is different than this training set. The training set is publicly available. They have about 1,559 images, which contain 2,257 parking signs, and the validation set contains 375 images, which contains 606 parking signs. Now we start building model. First, we take a traditional computer vision approach, which is a sliding window. It slides the window on the image and computes some kind of a features called hog features. And based on that hog features, we train a linear SVM classifier to classify those patches, those windows about the parking sign. So it's very straightforward. So we take a windows of 96 by 96 size and compute hog features for each window in different color spaces and train a linear SVM classifier. In order to improve the model performance, we perform a couple of tricks after the classification. We use non-maximum separations, and then we also use the hard negative in mining approach, because this is the imbalanced data sets where we have very few parking signs as compared to other background. So we try to penalize the negative samples, and then in order to make better predictions, we also use fast detection as a negative sample with high weight to bias the classifier towards the positive class. But these models are not working well. Then we go into the deep learning models and we try two famous architecture. One is Yolo and other one is the SSD. The Yolo is you look only once platform. We use the darknet 19 classification model, which have mostly 3x3 filters. It also have batch normalizations, 19 convolutional layer and 5 max pooling layer. Initially train the model on the ImageNet, which have 1,000 categories. And then we use transfer learning first to remove the 1,000 categories. And then we add 3x3 convolutional layer with 1,024 filters followed by 1 into 1 convolutional layer with the number of outputs. And then we go for fine tuning this whole network again with epoch of 160 and learning rate start at 0.001 divided by 10 at 60 and 90 epoch. We have a one flow convolutional model for the object detection. So in this model, we predict category scores and box offset by a fixed set of default bounding box. And the fixed set is about 7,308 boxes. And then we use convolutional filter applied on each feature map. Prediction of different scales from different maps of different scales, and separate prediction by aspect ratio. So we also try to end-to-end train and find high accuracy. So there is a comparison between the speed and accuracy between the Yolo and SSD. Both are single flow framework, but SSD have high accuracy, little bit compromise on speed. Yolo have high speed, but they have not as accurate as localizing the parking sign. So SSD model, they perform detection of parking sign on average 5 images per second. The Yolo, they go for more than 50 images per second. Here is the architecture of SSD model. So we have initially VGD model, and then we have a multiple convolutional layer after that, and each convolutional layer get output to the model, because those are the, we basically extract feature at multi-scale. So we have getting the feature map at different scales. And also in order to cater the different aspect ratios, so we use different feature map and try different aspect ratios at different feature map to try to predict objects with have weird size and shapes. So here's the active learning framework that we start with. So it basically start with randomly selecting 50% of the images that we get from the download images. The images that we select for the San Francisco city, so we take the center point of the San Francisco on the map and take a radius of about 10 miles from the center point and compute all the images within that boundary. So the number of panoramic images that we download from those this area is about 13,000, and from that 30,000 panoramic images, when we divide into small tiles or chips, it become around 4,000 and 4,000 K images. So from that we select 50% images randomly, and then we launch our job to review and find the parking spot in those 50% images and label for the box for each parking spot and train our deep model. And then we test the accuracy of the deep model. If its accuracy are below the threshold that we set, and then it go for another 2% of images, and this time the 2% is not randomly, 0.2% not randomly, but it's based on the model's performance on unseen data. So we divide the prediction on unseen data into 3 subsets. One is the high confidence images, which have a confidence score of above 80% to detect a parking spot in that image. And from that, we select 20% of the images with the lowest confidence score within that subset. And second subset is the low confidence images, which detect the parking spot, but with low confidence, which is less than 80%. And from that subset, we select 60% images with a highest confidence score. And the last subset is there's no parking spot in the image, and from that we randomly select 20% of the images, and it go again to labeling and then training the model. And then from the trained model, we create 3 subset: high confidence, low confidence, and no prediction image set, and then again find the new cases for the training the model. Here is the framework diagram. So we start with the street view data set, and then we locate the panoramic images, we tile it, we go with crowd labeling, we train the model, we divide into high and low confidence data set and non-prediction data set. From that, again go for active learning with 0.2% of images, labeling, and again training the model. So here's the number of the data in the different training set over the period of time that we found. So on the second column, number of images, and the last column is the number of annotations. The first one, addition of new images, and then total number of images, and the addition of new annotations for the parking spot, and the total number of parking spot in that data set. So we start with the first training set, which have 500 images and which contains 704 annotations. After a couple round of iterations, we found total images about 2,900, and the number of parking spot that we found is 4,444. Here's the performance of the model in terms of detection of the parking spots, the true positive, false negative, false positive, recall, precision, and F score, and intersection over union. You see, over the period of time, the model is predicting parking spot with high accuracy and with more confident in terms of intersection over union. This is the plot between the model loss and the model accuracy. The loss is the loss of the deep model. So it started with first iteration of active learning, and then over the period of 7 loops, so it starts decreasing. And the red one is the validation loss, and the blue one is the training loss. Here is the intersection over union is the blue in color, and F score is red in color, and it try to improve over when we have more iterations of active learning. So here's the few example of the model Yolo and SSD. The Yolo, they are detecting the parking spot, but they're not more accurate in localizing the parking spot. SSD, which are very accurate in localizing the parking spot. So the only challenge with Yolo, when we have multiple parking spots in a same pole, then it's very hard for them to identify how many parking spots there. But SSD, they are very efficient to find the number of parking spots on one pole. If they are like 4 or 5, they are almost detecting all the parking spots in that pole. Here are a few challenging cases when the position of the parking spot is very weird. You cannot see properly here. This is about almost less than 10 degree of angle, and here the parking spot in the there are some sign on the building that look like parking spot, but there's not parking spot here. So these are some challenging cases that where models struggling to find the parking spot, or maybe mistakenly find the parking spot. So, and then next problem is we train the model on the San Francisco data images. So how we can generalize the model, or we can try with other cities. Sometimes, most of the time, the parking spot are same, but sometimes they have different parking spot in each state. So we tried our model on different data sets, New York and Los Angeles, and we found same level of accuracy. And then we find when they detect the parking spot. Those are the images, parking spot that are not defined in the San Francisco parking sign database. After finding the parking spot, the next task that we are targeting to find the rules from those detected parking signs. So we try now the Google API to translate the text from the parking spot. And this is just try and the Google API, but in future we are building our own API to find the rules from those parking spots and build a database of rules: when you park, how long you park, which day you can park in a specific position. So, and the conclusion, so improve. So basically, we are trying to use the active learning framework to improve the problem that we start with parking sign detection, but it can be generalized with other problems. And you can guess that the total images is more than 500k images, 4.4k, 440k images. So from this big pool of the images, so we just start with a couple of thousand of images and go with loop of active learning. And after 6-7 loop of active learning, every time we're adding couple of hundreds new images in the database, and we find a accuracy of more than 85% detecting the parking spot in the images. Is we try to form the parking spot using template and prior knowledge, and also in future we're trying to extend this platform for parking meters, and also extract the curbs where we cannot park the vehicle. There's no unique solution or technology that can solve parking problems, but we can try different ways. This is one that we tried. And also, self-driving car are getting ready for ride-share services, but they will be operate in a human world. They need to have maps of parking spots and rules and the ability to see if a parking spot is vacant and occupied. Thank you. Now I take a couple of your questions. So there's a question from Fengzu. How did you come up with the threshold and the sample ratios to select new samples for the training? So at this point, I go with heuristic. I try few numbers, and then the number that sounds better, I select it. And the threshold, I'm not sure what threshold you're talking about. I'm talking about the selection of the training sample. So okay, the threshold is about the confidence score. So I try confidence score with different levels from less than 80%, 70%, and 60%. So I found, and this number give me better to converge the model. Second question, how did you handle false positive if the model is confident a patch is a straight sign, but it is incorrect? Want that patch remain in the training set? Okay, so to check this problem, so we have that's why we create three subset. One is the high confidence. It might possible that it detect a parking spot in the high confidence with high score, but that are not parking spot. So we review those images with the crowd labeling job. So whenever we go into trainings, we get our training data. So we always go with review with crowdsourcing, and that authenticate the model performance. It's not blindly we are selecting all the images from those subset. Other question, could the speakers post the link of his slide and script here? So I'm not sure about the code. I will check with my company, but the slides I can share it.
Yeah, for the slides, I can share it in the post-talk emails. I will send the link to everyone.
The data set is public. The first set of data is publicly available. You can go on our website. The slide is publicly available. The code, there's not the very sophisticated code. It's just general object detection and classification code. You can find similar kind of code for different models. But I will check with my company if they are okay. I can share the code. I will take another question. What were the most difficult cases from the model to recognize for the parkings that weren't parking sign? So they're human-made objects that look like parking spot. It's very hard for the model to detect that those are not actual parking spots. So there are many signboards in San Francisco that look like parking spots. So, and sometimes people, they have parking spots. Sometimes people, they stamp some stickers. They spray on top of that. So those are the cases where it's very hard to find the parking spot. But there are other solutions for such kind of problems. Then we are going to another domain where we are using this special information. So normally in most of the cities, they have same rules of parking in a same street. If there's one parking spot which is not properly detected, either because of the collision, tree on top of that parking spot, or maybe someone painted or someone make a sticker. If we have parking spot in the same street detected correctly, so we can generalize what are the rules and what are the regulations for the parking in this line. So we are basically building a special database where we can estimate the parking rules with neighboring parking spot as well. Okay, I will take another question. If you have a question, you can. Okay, this is I'm the organizer.
I think there are two more questions over there, right?
Okay. How dependable are the crowdsourcing labels? How often do they make mistakes? So here's the question. So I have done a couple of studies using the crowdsourcing to build machine learning model, and I have done with medical data, which is more challenging task. So I have a paper in 2014, which I used the same figure eight platforms to label for the nuclei detection and segmentation, and then check with the experts, medical experts, pathologist levels, and I found out about more than 85% they are accurate in detecting and segmenting the tasks. And the other recent studies that I published last year in Nature Scientific Report Journal, and that's about the classification of immunohistochemistry images for the protein expression. So it's basically detecting the ER positive and ER negative cases for the cancer. So in that studies, I also get the about 86% of accuracy detecting the ER positive, ER negative in histochemistry images. And here the gold standard are the expert pathologist labels. So this is the what I have done in couple and publish it, and those are paper publicly available. I think their dataset and code is also available somewhere on my GitHub. But my point here is, so if you launch a job initially, maybe you not get the high accuracy, then you need to describe the how you can take the data and how can label the data. Instruction play a very important role. Instruction and the example play a very important role to educate the crowd how they can label correctly the images. And then we have in our figure platform the checks how we can validate that crowd is labeling tasks rightly or wrongly. So we are getting the data when they're labeling. Based on that, we can guess that these are the correct label and these are not correct label. And the other point that we use is not only one label for one image, we collect multiple labels for the one image and try to aggregate. So it's kind of wisdom of the crowd. So then if there's some person who have mistake, but there more people who are rightly judging the label, so in this case, we can also minimize the mistakes from the crowd. Okay. Is there a link to that study that you could provide in the post email? Okay, so I will send to the organizer the papers that I publish with this crowdsourcing, so you can get those papers. Can you suggest some of the good resources to learn for beginners in the field of computer vision? So in computer visions, there are a bunch of things. Some are related with domains and some are related with the technologies. In domains, they are like medical domain, self-driving cars, satellite images, drone images, retail and fashion images. And then in terms of computer visions, we have object detection, image classification, object classification, segmentation of the object, and then the activity recognition, and then the captioning of the images. So there are a bunch of different problems in computer vision. So if you would like to get state of the art, one way is you can subscribe yourself for monthly magazines for computer visions. In that magazine, they overview recent paper with their own feedback, how those methods are working and how they are addressing the problem, what are the limitations of the method. So I can also send in the name of 1-2 journals, the magazines, to the organizer, and he can share with you all this content. And then you can also read blogs and then the blog posts from the different scientists. Okay, and the next question is about which computation tool and software do you use? Okay, so I mostly now use mostly Python and TensorFlow, but I also try PyTorch. So which have like these are two known and as well as mostly used in the research as well as in the industry. So Python is a language to code, and then in terms of deep learning framework and machine learning framework, scikit-learn, PyTorch, and the TensorFlow, these are the famous libraries or tools for deep learning. How is like the convolutional layer when creating a deep learning architecture? So it really depends on the problem and the data. So if you have a data set which is not the problem is not complex, the class is not complex, you are basically detecting cats and dogs in the images, which is a very simple problem. In that you don't need a large number of layers and large number of features from those layers, because those are, we can find the characteristic of the objects in with few number of convolutional layer and with less number of filters. But if you going other step of the problem, which is the classifying the breeds of cat or dog, which is harder problem. Then you go a details of information. If you look in the image, you need to go into the how the shape, eyes, color, and pattern of the skin of the cat or dog different. For that specific problem, then you have more conventional layer, high number of filters, more depth and deep models you need to design your model. So in that case, you have more in-depth architecture. So there are multiple parameters that you need to select. And other one is the hyperparameters, batch size, learning rates,